Okay, in a problem like this, what's really most important is that you understand what's going on and why you're doing it, because this is sort of the theory for that undergirds the rest of the class. So what they're doing is they're starting in the problem that I'm working here. They have a sample that consists of four values, 2, 3, 4, and 5. In part A, they want you to list all the possible samples that can be taken from that population of values and then compute the mean of every one of those samples. So if you have the numbers 2, 3, 4, and 5, and you have them in a hat, you could stir them up, pick out a 2, put it back in, stir them up again, and get another 2. So you could get a 2 and then a 2. Or you could have gotten a 2 on the first draw, put it back in, the second draw you get a 3. Or you could get a 2 and a 4, or a 2 and a 5. Or you could have gotten a 3 first, followed by a 2, 3, 4, or 5. Or you could have gotten a 4 first, followed by a 2, 3, 4, or 5. And finally, you could have gotten a 5, followed by either a 2, 3, 4, or 5. So in the top part of this on each one of these, the part that they have listed here already for you, those are just all the possible samples that might have been taken from the population 2, 3, 4, and 5. Then they compute the mean of every one of those samples. So the mean of 2 and 2 is 2. The mean of 2 and 3 is 2.5. The mean of 2 and 4 is 3, and so on. And then when they, on the next part, it says, what's the probability that a specific sample will be selected? So for every one of these samples, they're equally likely to occur, and there's 16 of them. So for any one sample, it would be 1 out of the 16, which is 0.0625. And then they want you to do a sampling distribution table. Now let me make sure we get some distinctions here. We had the population, 2, 3, 4, and 5. That's the whole population. We could compute the mean and the standard deviation of that population. Then we have individual samples. And when we're really going out later this is the theory part, but when we get to where we're collecting data and stuff, we're really just going to get one of these samples. But what we're doing now is we're saying, even though we only have one sample, but how can we put this in the context of what we're going to call a sampling distribution? That's what's coming up just now. So we have the population, the sample. The sampling distribution is the distribution of these sample means, of all the possible sample means that might be constructed from samples of size 2 drawn from the population 2, 3, 4, and 5. So of those 16 possible samples, only one of them had a mean of 2. There it is. And of 2.5, we had one here and one here, so that's 2 out of 16, which is 1/8. And then coming over to 3.5, we have 1, 2, 3, 4 of those divided by 16th is 4/16, or 1/4. If I were working this out, I probably would have, just to make things simpler to understand, have written 1/16, 2/16, 3/16, 4/16, 3, 2, and 1/16. But they've gone ahead and simplified it here. I actually would probably put it in decimal form too, or would be another option. And then finally, they ask you to graph the sampling distribution. And it's, if you graph all of that, make a histogram. Remember, there were 1 out of 6, 1, 2, and then 2, 2.5s, and so on. So it's option C. So the thing to get out of this, we won't get, it doesn't have all of it in this thing, but no, this population is not a bell curve. It's 2, 3, 4, 5. It's a uniform distribution. But the corresponding sampling distribution, if you take large enough samples, and this really isn't, but you don't want to do the math for what it is. But if you take a population, collect all possible samples, compute a statistic from each sample, the resulting sampling distribution is going to tend towards a bell curve. And that's option C here. I'll go ahead and say while I'm here to finish what's called the central limit theorem. And the mean of this sampling distribution, the mean of all of these 16 numbers, is going to equal the mean of the population. And the standard deviation of these 16 numbers, the standard error of the sampling distribution for now it'll be sigma with a x bar on it. It's going to equal the standard deviation of the population, whatever that is, divided by the square root of n, in this case 2. So the whole central limit theorem has three ideas. The sampling distribution has the same mean as the population. If you take the standard deviation of the population, divide it by the square root of n, which is 2 in this case, that'll give you the standard deviation or standard error for the sampling distribution. And most importantly, the shape of the sampling distribution will be a bell curve. Where that's going to come into play means we're going to be able to use the z-table for any sampling distribution, no matter the shape of the population. So as you're working through this and the remaining problems in this section, focus on those ideas and how they fit together.